Okay, we're going to talk about sound. We'll start with the good old philosophical question. If a tree falls in the forest and no one is there to hear it, does it make a sound? I have to say my initial answer to that is always yes. Like, of course it does. It falls down and airwaves rustle and move about and it makes a sound. But some of the definitions of sound, or the definition we're going to talk about of sound, involves three components of sound. The generation of the sound, that would be the tree falling. The propagation of the sound, which would be the sound waves traveling out, that were the sound waves that were created when the tree fell. And then the reception of sound, how we hear the sound. So if truly no one was there to hear the tree in the forest, it maybe didn't fully make a sound. It just made some variations in air pressure that moved out as waves from that point. Now we could argue that there was a squirrel somewhere or something that heard the tree fall. But that makes the point. So there's three things we have to have for sound: generation, propagation, and reception. And those are the things we're going to talk about this week. Aristotle realized way back in the 300s BC that sound needed a medium in which to travel. So the most common medium that we think of is air, right? Most of the sounds we hear travel through air. Sound also travels through water. If you're underwater in a pool, you can hear things. What are some other things that sound might travel through? It can travel through the ground, the images in the old Western movies where someone puts their ear on the ground and they can hear the horses coming from far away. Or the train tracks or whatever. So sound can also travel through solid objects, if they have some room to vibrate. And then there's the line from Alien: in space, no one can hear you scream because there's no air in space. It's a vacuum. Which brings up one of the problems with all men of my age who know about sound as we watch the Star Wars movies. And there's all this sound that happens in outer space. And if you think about it, it becomes very problematic because TIE fighters wouldn't make that sound in outer space, and the lasers wouldn't make that sound in outer space. Although I did hear one apologist present the idea that the Millennium Falcon was just so advanced that it had sensors that sonified the TIE fighters. So as Luke and Han were sitting there shooting at the TIE fighters, you could hear them because the sensors of the Millennium Falcon would find where they are and make sounds that Luke and Han could hear to interpret that. So I'm going to stick with that. It makes me feel better about myself. Okay. So Aristotle realized we need a medium through which sound can travel. Sir Isaac Newton realized that sound travels as a wave, and there are mathematical rules that govern how waves behave. So a sound is alternating waves of high and low pressure. In our case, we're usually talking about air pressure. So these high pressure areas are called compressions, and the low pressure areas are called rarefactions. So if you think of a spring, right, the spring compresses and rarefacts. It gets tighter and looser and tighter and looser. So that's sort of how a wave works. You've seen that in water as well. The water goes up and down. The spring, a jump rope. Usually at this point in class, I pull out some sort of rope and give you an example. I'll take this phone charger cable here, and you see when you move one end, it sort of moves in this wave-like function. That looked way better in the front of the class. Doing that in my weird little chair here is odd. So imagine we have a drum head. All these little black dots represent air molecules. When we hit the drum head, the air molecules spread out. The head moves downwards, there's more space. So that's rarefaction. The head gets flat again, equal and opposite reaction. The head of the drum moves up, the air molecules compress. So they get close, which pushes on the ones that are here, so that makes them compress. Then they compress and spread out and compress and spread out. And that's how the wave travels. So what's happening is the wave of pressure is moving. The actual air molecules aren't traveling. They're oscillating in place. So they get close together and push and get farther apart, right? But if the air molecules actually traveled, every time you heard a sound, you would feel a breeze, right? Or you would be able to smell the coffee of whoever was speaking, if the molecules from my mouth were going all the way to your ears. But they're not. They're bumping up next to the molecules, next to them, next to them, next to them, so on and so forth. So when we generate sound in a musical instrument, we need two things. We need something to vibrate and something to resonate. So on a violin, the vibrating string is the reed. You drag, or the string rather, sorry, I'm looking at the word that's not the word I'm saying. The string, right? So you draw the bow across the string, and that friction makes the string vibrate. And then the body of the violin resonates in a way that gives you the tone of that instrument. For a singer, what vibrates are vocal cords, or vocal folds, if I'm going to be correct. So we move air through the vocal folds, and they vibrate. What resonates? It's our body, our nasal cavity, the whole thing, which is why my voice sounds different than your voice, and your voices all sound different from each other, because we all have different shaped heads and sinus cavities and chest cavities and all of those things. On a trombone, my lips vibrate and then resonate through the body of the instrument. So every instrument, acoustic instrument that we have, has something that vibrates and something that resonates. So that's the first video on sound, and we'll keep going on the next one in a minute.